Today we will study about an interesting application and a device that allows this application to work in reality. So named the cyclotron, it's an interesting device invented way back in 1934 by two eminent scientists, namely M.S. Livingston and E.O. Lawrence. The original reason for coming up with a contraption of this nature was basically to accelerate ions or charged particles to very high energies so as to then collide them with other particles, with other microscopic particles, and then study the nuclear structure from the resulting collisions. So a cyclotron is a device that takes advantage of the combined behavior of charged particles in the presence of an electric field and a magnetic field. So in the last video lecture, we discussed how charged particles behave in a combined magnetic and electric field. So typically when these fields are placed perpendicular to each other, we discussed the unique case wherein the two fields, the magnetic field and the electric field, were placed perpendicular to each other and the charged particle was made to travel in a direction that is mutually perpendicular to both these fields. So a simple case where these two fields, the electric and magnetic field, are perpendicular to each other is a case that we refer to as crossed fields. So crossed fields is the principal basis on which a cyclotron is designed. A cyclotron is a simple device that is made out of two semicircular discs. So the discs are chosen such that they are part of the same circle and there is a small gap in between the two discs. Now since these two discs resemble the shape of the letter D, they are sometimes also referred to as the Ds. So effectively speaking, as I mentioned earlier, a cyclotron works on the principle of crossed electric and magnetic fields. So ideally what's done is charged particles are dropped right at the center of these discs. Now the moment a charged particle is dropped over here, the magnetic field that's present in both the discs starts acting on it and it starts executing a circular motion. But the moment it completes half circle, it arrives at the interface of the two discs, and it's here that an electric field is applied at the interface. There is no electric field applied anywhere else, there is only magnetic field elsewhere, but at the interface you have an electric field applied. And this electric field is such that when the particle is moving here, over here, this particular plate is kept at a lower electric potential as compared to this plate. So what happens is the particle moves across this interface but also gains extra velocity. It gets accelerated between this interface. So what happens is, by the time it has finished covering this interface, it has got accelerated, and because it has got accelerated, the moment it comes back to this disk, there's only the magnetic field acting on it. So it again executes a semicircular motion. But this time, the semicircular motion that it has executed has a larger radius compared to the initial semicircle that it executed. Again, it reaches this interface over here, and again it encounters the electric field, which is now applied with the polarity reverse, so that this particular plate is at a lower potential compared to this plate. Again, the particle accelerates across the interface. Since it accelerates, the next semicircular motion it executes has a slightly larger radius compared to the previous circular motion it executed over here. This again repeats over here. So effectively speaking, the particle after each revolution is executing a motion that is making it go further and further away from the point where it was dropped. So eventually the particle starts moving round and round such that it eventually reaches the very edge of the disk. So suppose if this distance is, let's say, capital R, or the radius of the two semicircular Ds, then it eventually starts traveling at a radius that is equal to R. At this time, there is a separate magnetic field that is applied to the particle, and when it makes one final jump over here, this separate magnetic field that is applied over here causes it to come out of the cyclotron. It comes out of the cyclotron, and then we use it for whatever scientific application the accelerated ion or charged particle needs to be used for. So this is the basic principle on which a cyclotron works. Now, if we look at the mathematics behind this, you might remember that when we were discussing the working of a charged particle in the presence of a combined magnetic and electric field, we said that the reciprocal of the frequency, which is the time period, was given by 2 pi m divided by q into b. So this was the mathematical equation we derived in the last video lecture. So this equation, you might observe, gives the time period for the charged particle to complete one complete revolution. So t is the time period to complete one revolution. And the time required to complete one revolution, whether the particle is here or the particle is at the edge of the cyclotron, is independent of the radius as well as the velocity of the particle. Quite an interesting observation that you just need to make note of. The time required to complete one revolution, whether the particle is at the center of the cyclotron or at the edge of the cyclotron, no matter how big the cyclotron is independent of the radius of the path, and it's also independent of the velocity at which the particle is moving. which means it's only dependent on its own mass and the charge on it and the intensity of the magnetic field applied. The other thing that you will also see is that I was talking to you about the fact that an electric field is applied at the interface of these two Ds. Now I said the electric field applied at this point when the particle is over here is such that this particular plate is at a lower electric potential, and when the particle arrives at this point, this plate will be at a lower potential. So alternatively, as the particle is making its motion, the plates have to be reverse polarized. So if this was at a lower potential at one point of time, by the time the particle has finished T by 2 revolution or half a revolution, then the other plate has to be at the lower potential. So this has to keep fluctuating constantly at a speed that is equal to the speed at which the particle is completing every half revolution. So basically what we are saying is that if this I denote as Fc, or the frequency of the cyclotron, so what is the frequency of the cyclotron? It is the number of times a particle is completing rotations, number of rotations or revolutions that it's completing in 1 second. Now this frequency of cyclotron or Fc should be equal to what I call Fa, or the frequency of the applied voltage. So the applied voltage of the electric field between the two semicircular discs, should be equal to the frequency of the cyclotron, or the number of revolutions that the particle is completing in 1 second. So why should this be the condition? Because it is only when this condition is met that the particle, as it arrives at the interface after completing half a revolution, it finds itself exactly encountering the condition where it has to jump between this plate and this plate, and during the jump its energy gets increased and it accelerates, and with that accelerated motion it continues for the next half revolution, where it again encounters a reverse polarized field and it again jumps, again increasing its energy. So as it keeps making successive jumps, once here, once here, once here, once here, its energy goes on increasing, and since its energy goes on increasing, the radius goes on increasing. The radius of its motion goes on increasing. So this particular condition is what is called as resonance condition. When Fc, cyclotron frequency, is equal to Fa, the applied voltage frequency of the electric field, then the condition is referred to as the resonance condition. Now, what is the energy being imparted? So we know that the kinetic energy of a particle is given by half mv square. And we also know from our previous discussions that v, or the velocity of the charged particle, was given by q b r, where r is the radius. I'll come to that in a minute. Q b r by m, where r is the radius of the circular motion it's executing. I have taken this as capital R because I am interested in the velocity of the particle when it is completing its last revolution, when it's revolving at the very edge of the disk, just before a separate magnetic field kicks it out of the cyclotron. So what is the velocity at that point of time? That velocity is given by QB into capital R divided by M. So if I substitute this back in this equation, I am going to get my kinetic energy as half m into v square. So it's q square b square r square by m square. So a little simplification gives me q square b square r square by 2m. So this is the total kinetic energy that the particle possesses at the point of it coming out of the cyclotron. So what are the applications of this particular cyclotron? So cyclotron was basically, as I said, invented by the two scientists Livingston and Lawrence to initially study nuclear structures by accelerating charged ions and getting them to collide with the nucleus of an atom, and in the process find out how does the nuclear structure change. That basic reason for which cyclotron was invented is still very much valid today, and today we have huge cyclotrons wherein the radius, the R radius, goes up to several miles, like the one we have in the at Switzerland at CERN. So this is one of the world's biggest cyclotrons, wherein the radius itself goes to about a few miles. So these modern day cyclotrons, or the other one, the Big Hadron Collider, what we also call as the BHC, the Big Hadron Collider is another big one. So these modern day cyclotrons have helped physicists unravel a lot of microscopic particles like bosons, leptons, quarks, and several more, allowing them to study nuclear structures at an unimaginably microscopic scale. Also, cyclotrons are also used to accelerate ions so that they go and get stuck with existing nuclei to produce new types of materials which can be used for medical and other related research fields. So these are two basic applications for which cyclotrons are mainly used for.